Ho visto che c'è una sede di assistenza solo di università, quindi c'è 70 minuti di spiegare di come deve essere un
sì, giusto i 6 gli ultimi 10 secondi che hai Right. Can I start?
Sure.
Welcome
We're
back.
ready. On tape.
So we'll let me just recap what we did yesterday. Yesterday we started looking at the quantum corrections to super QCD, and we sort of noticed that it's although it seems like a daunting problem. Thanks to the technology that has been developed in the 90s, there are some simple tricks that allow you to actually get a lot of mileage in understanding the structure of the holomorphic quantity. So, in particular, we saw the example of super QCD with NF strictly less than NC. We had seen before that classically you had a bunch of moduli, which were the mesons, and F times NF complex matrices, so they belong to this complex modular space. But we saw that quantum mechanically, by imposing that, the only thing, I didn't write the lambda and everything, but the important thing is the dependence on the meson. By imposing that the superpotential generated was respecting all the symmetries of the theory, it was holomorphic, and everything, we saw that there was this unique choice for the superpotential. And this, by the way, means that the theory in itself, if you don't add masses, is unstable. It simply means that since the superpotential, and in particular that there is no quantum modular space. The quantum modular space has gone away. In fact, there is no theory really, because you see, the superpotential is going inversely proportional to some power of the fields. Now, if this is the only thing you have, let's take an absolutely trivial example, where this is a 1-by-1 matrix, say. Suppose you have a superpotential that goes like 1/5, say. All right. Then, of course, the V, which would be then the derivative of the superpotential with respect to phi squared, this goes like 1/5 squared, phi to the 4th or something. And so this is the derivative of this guy, and that's pi squared, so pi squared squared to the 4th. And so clearly, the theory is driven to higher and higher values of this field, and this is just a multidimensional generalization of that. And so there is no, this is called a runaway vacuum, because the true V equal to 0 state occurs at infinity, and so the theory is essentially unstable. Okay, so now we want to move on to more interesting cases where NF is equal to NC or larger than NC. To do that, it's actually worthwhile to stick with this and put in something that is of interest anyway and will be useful for the following discussion, which is adding mass. So I told you that this is the superpotential for NF equal less than NC, and that the theory becomes unstable, but this is in the case of a massless theory. Now let's see what happens if we add a mass. So suppose I add now, we're still in this context, although some of the results will actually be valid more generally. So I will take now the total superpotential to be the superpotential that I will get if I added a mass for the quarks, which is I introduce a flavor matrix FF prime times Q tilde, F prime F, C's. Okay, so this is a flavor matrix, which is a mass matrix for the quarks. Okay, and this is the superpotential that gives a mass to the thing. Now I'll just drop all the indices because now we are all used to the matrix notation, and I put a trace. Okay, and the trace is on the appropriate things. So this is the only normalizable superpotential you can think of in the case of fields in the adjoint and in the fundamental and anti-fundamental representation. So you will have this, which is the three-level superpotential. And then you will have the non-perturbative one, which is the one that we have written before. So, well, now I might as well write it in its full glory with the lambdas and everything. It's some constant which can be fixed to 1, 3, and c minus nf. The determinant of m, 1 over nc minus nf. And of course, so if I had gone to the infrared, then I don't think of q and q tilde as my degrees of freedom, but I'm thinking of the meson itself. Okay. And this is the W non-perturbative. And there is nothing in between. You can replace the same argument as you had before to show that there are no perturbative corrections to this thing. And so this is the exact final answer. Now you should ask me a question. So now I'm asking you a question, and let's see if you know the answer, because I told you the answer yesterday. So if I put in a mass, I'm breaking some of the flavor symmetries, right? Remember, just like in QCD, if you put in a mass for the quarks, the chiral symmetry is broken, right? This is exactly the same thing. I put in a mass for the quarks, for the superfields, and so I have broken, this mass has broken this SU and F times SU and F prime, or SU and F tilde, that was used to derive this thing, right? So now my question is, well, then what? What's wrong? I mean, am I doing something wrong? Or how can I argue that this is still okay, that I can still use the full chiral invariance even if I put in a mass to derive this thing? Because otherwise you could say, well, if you put in a mass, say a diagonal mass, then this thing breaks out to the diagonal, then you could start using traces here, right? Like we were saying yesterday. But no, I don't. Why?
Are you including a scalar field in your multiplex or not?
I'm sorry?
Are you including a scalar field in your multiplex or not?
Scalar field in what sense?
So this mass term is divided by hand with breaking, as you said.
That's correct. But you're thinking of the trick of yesterday, right?
Yeah.
Right, that's exactly the point. So, but if I think of it as a chiral superfield, and this being the scalar vacuum expectation value of that chiral superfield, then I can actually give this mass transformation laws under SU and F cos SU and F tilde, and that allows me to do this kind of argument just like we did yesterday. So once I have this object, it's a nice exercise now to find out. Now, intuitively, I hope you realize intuitively that here we have so remember the potential is the absolute value of the gradient of the superpotential, right? So here we have something that tends to go down like this, but here we have something that will tend to sort of stabilize this thing a little bit. So, in fact, this theory will have supersymmetric vacuum. It's actually a cute exercise to derive them. It's simple matrix algebra. I will just, so when I write M, now I'm thinking of M as a big matrix, okay? And if you do this thing here and you take the derivative, this becomes, let's do it for the NF equal to, let's do it for the NF equal to NC plus 1, which is the easy sort of, it's the nice case. So for NF equal to NC minus 1, sorry, then this funny exponential goes away and this becomes 2NC minus 1. Right? So I want to see if there are supersymmetric vacuum. I claim that this is the derivative of this. play with the determinant and convince yourself that this is the derivative of that term. Now, the first thing I can do here, so if I want to find vacuum, I have to find solutions. I have to find m's. I have to find a matrix M, an NF times an F matrix M, that given a constant matrix, now M, little m, you can think of little m as a constant, really, times a diagonal matrix. It doesn't have to. Now, so I have to solve for this. I start by taking, for instance, the determinant of these things, and this gives me, and this gives me that the determinant of m times the determinant of m is equal to 1 to nc minus 1 over that m nc minus 1. nc minus 1 is an f, so that's why I bring m to the left hand side, I put the equal sign, and I take the determinant of both things. This is just the identity matrix, and so it is raised to that. This actually put back, now that I have the determinant, now I can solve for the determinant of m, and I put it back here, and this actually allows me, again, it's a very simple calculation that you can play with, and
This is 2nc plus 1
Yeah.
say if you find a mistake, say it, but I think it's
2nc plus 1.
Just one again.
It would be 3nc minus nf.
so. This one is 3nc minus nf, which is equal to 3nc minus nc minus 1, which is 2nc plus 1. Why did I write that? Thank you. So it's probably wrong in my notes as well. Yeah, there's been a phase shift between plus and minus 1 and between going from one line to another. Sorry about that. Thank you. That means you're paying attention. Very good. I did it on purpose, of course. To see. So anyway, at the end of the day, you get that. So this is just matrix algebra, and you get the full answer is that m is equal to m to the minus 1, determinant of m to the 1 over nc times lambda to some power, which I guess is now the phase has gone back to plus. Good. Right. So that's your final answer. So given an m, you do in fact find solutions that are supersymmetric. How many of them? This is interesting. So you do have a set of supersymmetric vacuum, but it's a discrete set. And in fact, how many of them do you have? You see, there is a square root of 1 over nc here, given an m. So given a determinant of m, so given a little, there are lots of m's, given little m, given the mass, I can compute the determinant, and the nth root of that will give me, of course, a choice of nc possible solutions. So I have, in this space of determinants, I have a possibility of having nc different vacuum depending on which branch of this root I choose. And this is actually what is expected from a completely different argument that we may see in another contest tomorrow or next week, which is namely so this is a very nice consistency check, namely the fact that if I give a mass to all of my quarks, imagine taking this little m to be a diagonal matrix as I did before. That means that I am lifting all the quarks and squarks fields from zero mass to a higher mass. So in the very, very low energy limit, this theory will actually be pure Superyon-Mills. Right? It will be a theory with no matter, just with gauge matter, because all the matter fields have been raised to a certain mass. Now, so that theory is known to have NC for SUNC and to have NC vacuum. This comes from the computation of the Witten index for pure Yang-Mills theory that we will mention later on. So this is a nice consistency check, and it matches with the fact that for pure young meals, so what I'm saying is that if I have a mass that is non-zero, in the infrared this theory becomes pure super young meals, meaning gauge with no matter. And for this one, there is this Witten index formula that if you haven't seen, we will mention it tomorrow when you start looking at it, that says that for these theories, the Witten index, for a pure gauge theory, the Witten index is 1/2 of the index of the adjoint representation, also called the dual Coxeter number or something like that. And in our case is NC, because this is 2NC. Okay? So that's great. So this is a nice consistency check. Now that we've done that, we can go on, and this is getting more fun, we can go on to the case where NF, so the bottom line is the theory does not exist in the massless limit, but it does exist in the massive limit, and it has NC vacuum supersymmetric. Okay? Now let's look at the case where NF is equal to NC. So since I have two numbers that are the same, I might as well call them N. So from now on, for a while at least, until I tell you otherwise, I am using these numbers, these symbols interchangeably. I try to write N all the time so that you know that it's either one or the other, they're the same. Okay? You remember the classical theory. The classical theory had this field, the meson, which is always there. And then there was a baryon and a baryon twiddle, an anti-baryon, that had just one component, right? These were the determinant. This was the determinant of Q. Q is an M by N matrix, and this is always Q tilde. Good. Now we saw that, well, we started with this theory, and we looked at the moduli space, and we saw that the classical moduli space was characterized by the trivial algebraic relation that B tilde is equal to the determinant of Q. Or let me write it, the determinant of M, minus B tilde is equal to 0. This is the classical modular space of the theory. Now, the game, remember the game. Now we want to look at the quantum corrections without doing any work. So we introduce lambda now. And we want to see, first of all, if we can write a superpotential. Maybe there is a superpotential generated, just like in the previous case, maybe there is a superpotential. Let's check that. So we want to write a superpotential in terms of lambda, B tilde, and M. Okay? Is it possible to write a superpotential in terms of these guys? The answer is no, for the very simple reason that if you look at the table that I had yesterday, that I will not rewrite, let me just double check that I'm not talking crap. Because right, yes. If you look at the table that we had yesterday, you see that the R charge for an F equal to NC equal to N, the R charges of this object, well, this is 0 because the R charge is not anomalous. We can always think of lambda as a even this one can be thought of as some kind of, depending on some kind of superfield, but still R charge equal to 0 because the R charge is not anomalous. The R symmetry is not anomalous. But then if you check the R symmetry of these guys, they're all 0. This means that there is no way I can take a function of these guys and get something that has R charge 2. Right? The superpotential has to have R charge 2. And so it's not going to happen. So this proves immediately that the non-perturbative superpotential for this case is 0. Are we done? No, because we have to check the superpotential is not there, but there is another quantity that is holomorphic that we should check whether it's getting affected or not. And it's right here looking at us. This quantity here is the quantity that describes the modular space of the theory itself. It's described by an algebraic curve, which is a holomorphic, so some sort of complicated polynomial in these complex numbers. Right? So it is true that the superpotential is not changed, but the question is, could it be that the quantum modular space is different from the classical modular space? In other words, could it be that this relation is changed by the quantum corrections? And the answer to this, amazingly, is yes. And to see that, again, let's try to guess what kind of curve I could get. Right? What kind of difference I could, what kind of modification I could have from that thing due to lambda. So I have to find that. Right? So these are all our charge 0. Let's look at the dimensions. So again, we have, so I need something that is SUNF left, SUNF right, and B invariant. Our charge is invariant. So I can only make this, so the only two objects, these guys have baryon numbers, right? And I certainly want my equation, my formula here to have 0 baryon number. So it has to be respecting all the symmetries of the theory. So you can immediately see that really these are the only, as far as the fields are concerned, I can only play with these two combinations here, or anything that is algebraically dependent on these things. So the generalized equation. So if I say that, I don't know how to call it. Say the function, the classical function of M and B tilde that defines the modular space is this thing. Right? And this is what I set to 0 for the classical thing. But in general, the only possible dependence of M and B tilde is through these two objects here, because they are the only one that respect all the symmetries of the theory. So in fact, really, I can just think of the dependence as coming from like this. And now I have to ask myself whether there is a quantum deformation of this thing. That is allowed by all the rules of the game that I have. So let's see. Clearly I can come up with a lot of terms here. First of all, let's do a little bit of dimensional analysis. And what is the dimension of these objects? So the dimension of this is n, the dimension of this is n, and the dimension of, the dimension of m is of course 1, 2, because it's 2, there's a quark and equal to that. So the dimension of the determinant of m and of b tilde are both 2n. Alright, so at least dimensional analysis works. This is the same dimension as that. This could be a sort of very basic check that you should always, that they teach you in first year in school. You should always do dimensional analysis. That's okay. Dimensional analysis works. And so if there is any, so obviously then I will have to look for something here. The powers of lambda that will appear will be multiple of 2n, of course. So I will look for things of this kind. Since I cannot use any other things than this, if I want to add something that works out dimensionally, I will have to put some powers of lambda 2n. So let's play with it a little bit. So I could have, and the rule of the game is that when lambda goes to 0, I have to get this. Certainly. There are actually a couple of other things that we may want to check. For instance, suppose I write this. So I have to construct, let's try adding stuff. Alright? Certain things I certainly cannot add. For instance, I could take b tilde square divided by lambda to the 2n. Is this any good? No. Why can't I write this thing? What does it do? It doesn't work because when lambda goes to 0, this blows up. So this is certainly not a good quantum correction. Quantum correction is to go to 0 when lambda goes to 0. Nor I can divide this by determinant of m. These are all dimensionally okay. They're holomorphic. This doesn't work again because when lambda goes to 0, this remains. That's not allowed. Now this is allowed. Right. But strictly speaking, so is this. could write this down. However, no. The claim is that only the constant term is allowed. This is the refinement of what we were saying yesterday. So what I said yesterday was a little bit too slick, perhaps. It was that the only thing you have to do is to check when lambda goes to 0, you recover this. This is certainly a very important point, but you also have to check that. So first of all, when you're a freshman, they tell you never, ever, ever to send a dimension full quantity to 0, right? They kick you out of class if you say what happens, if you take a dimension full quantity to 0. Then once you get into graduate school, you start doing it again. So, but you shouldn't. So what I said yesterday was you send lambda to 0, right? Strictly speaking, lambda, of course, is dimension full quantity. What is meant is you should consider cases where the expectation values of the other fields, which in this case is BB tilde and ZM, are much larger compared to lambda. And in that case, you should check, if you have a theory with many fields, you should check that in all of these directions, so if you take all of these fields and you take them to have an expectation value that is larger, much larger than lambda, the theory should become classical again. So you should not introduce new vacuum or new physics, because it is the same thing as setting lambda to 0. So if you were to, so this term is allowed in a sense if you say, well, I want to let lambda go to 0, but it's not allowed in the correct sense of saying that there should not be any other solutions than this in the case where both determinant of M and BB tilde become very, very large, much larger than lambda. So the only thing that is actually allowed is this one. Okay? So in other words, you will always have something in the denominator, and this something in the denominator will become arbitrarily small if you go out to infinity in that direction, and it will introduce vacua that would be visible classically, but they cannot be there because lambda is small. Okay? So this is the only thing that can happen. And again, the question is whether this constant is there or not. So it could be a number here. Again, that thing is there. And to show that, you can do it in many ways. One slick way to do it, you can do it with instantons as well. There is an instanton calculation that gives you this. But a slicker way, I guess, is to go back. I will not go into the whole song and dance, but you go back to the NF equal to NC minus 1, and you realize that there is, we had, so for NF equal to NC minus 1, we had you put in a mass. Sorry, let me say it a little bit more correctly. So this is another game that you play all the time. I will not go through the whole algebra because it's simple algebra that you can work out yourself. But so now I argued so far that this is the only possibility, and there is a number here, little a, that could also be 0. And if it is 0, then we don't know yet. If it is not 0, then we can say that the quantum modular space is different from the classical modular space. If it is 0, then the theory is kind of boring and nothing happens in the quantum corrections. Now, so to argue that this number is not 0, you cannot really do it at this level. You have to actually do a little bit of a more detailed check. So the sort of hard, solid way of doing it is to see whether this is generated by instantons, and it is in a very interesting way that we will not discuss. A simpler check that is also a consistency check that works just fine is, which is something that you do most of the time when you play with these things, is you play, so another trick, so this is another trick, to show, for instance, that to fix some of these constants. Play with the masses. Go between some NF and another NF, go between NFs, two different values of NFs, by turning on and on, by turning on and off masses. So one thing you do here, for instance, you take the NF equal to NC theory, and you add to it something that we didn't have so far, a 3-level superpotential, which sure enough is the same as the one we had before, M. But now you take M, the matrix M, let me say it's a hat here so that it's a matrix, okay, whatever. This M, though, has only one entry that is non-zero. and everything else is 0. So now you can play with this mass, and you see, obviously, if this mass goes to infinity, being dimensional quantity going to infinity, you have to figure out what I mean. If this guy goes to infinity, then you go back to, of course, this, because you have removed one quark. And if this mass goes to 0, then you go back to this one. To do that, since you know the superpotential that you have to get, which is the n for nf equal to c minus 1, you can actually check that this thing has to be there. It's a nice computation that you can do, which I will not do because otherwise we waste too much time. All right. So the summary of the nf equal to nc case is that the quantum modular space is indeed deformed, and it's not the same as the classical modular space. And a nice feature of the quantum modular space compared to the classical one is that it is actually regular. It's smooth. It doesn't have a singularity at the origin. And also, so this thing here looks like a if you use your fantasy, your multidimensional intuition, looks like a cone. It has a singular point where all the normal. So remember that if I give you a surface embedded to check, the mathematical details may be somewhat sloppy, but to check whether it's singular or not, you have to look at the gradient, which defines the normal vector to the surface, and check whether it's well defined everywhere, right? And so the gradient here would tell you that, and then, so to check that you have a nice gradient, you have to take the gradient, so the derivative of this function with respect to all the fields. In particular, the only case in which it's not well defined is when all the fields are vanishing, because the gradient here would be all the m's and the b and the b tilde separately has to be 0. Now that point actually lies on this curve, is exactly the tip of the cone. So both the gradient of the superpotential and the superpotential are 0 at this point here, which is the point where m equal to b tilde equal to 0. So this is a singular point of the classical modular space. However, here, the gradient is still the same, because this is a constant, so when you take the normal, here is the same, but you're no longer on the modular space when everything here is 0. So the quantum modular space, you write it like this. It's smoothed out, okay, by this lambda, okay? And as lambda goes to 0, so this thing gets more and more singular. Okay, thanks. So now we have played n equal to 1. So n equal to 1, sorry, what am I talking about? We played nf equal to nc.
Just double checking I understood correctly. So lambda 2n is present not because there are instanton corrections in the nf equals nc, but because there are instantons in nf equals nc minus 1.
Both, actually. There is a nice paper, I believe it's Witten and Beasley, but there is where they actually derive. It's more recent than this thing. So this was a little bit of a mystery where this thing was coming from directly from the nf equal to nc. Now I don't want to say things that I may say slightly wrong, but you can actually get this directly from an instanton calculation. But they're funny. It's a little bit more sophisticated instanton calculation than your everyday.
Yeah, because these instantons don't give you a W non-preservative.
Yeah, right, yes. No, you have to consider multi-Fermion terms. I don't want to say it in detail because I don't remember exactly how it works out, but I can give you the reference. It's a very nice thing. So it works out. I mean, all of these things have been checked even to much deeper level than my superficial presentation here, of course. I'm just giving you the sort of... Right. Okay. So, right. So this theory actually is a nice example of how much more we know about supersymmetric theories than non-supersymmetric theories. Because remember, any point, any m and b that obeys this formula, that obeys this equation, is an honest vacuum configuration of our theory. So here you can actually impress your friends by telling them that you know a theory that has confinement but no chiral symmetry vector. It's a case where you can set that m to 0, and you saturate this by just taking b and b tilde equal to lambda n squared. So this keeps SUNF times SUNF tilde unbroken, and well, That's it. So as you move around, or you can have a theory that looks much more like QCD by taking that M. Say take M diagonal, set the values to 0. Then there will be the remaining critical modes that you can work out. And so by moving around this space, you can find examples of all funny kind of quantum behavior that wasn't even, before the 90s, wasn't even known if it could exist or not, and so on. So it's a simple theory that allows you to extract a lot of funny properties. So theories with interesting dynamics. They all belong to the same modular space. Every point in this modular space is a different theory. It's a different vacuum. It's a gauge independent, they gauge in equivalent vacuum. So you should treat them as different theories. Okay, so now I want to talk about the NF equal to NC plus 1. So we're slowly moving our way up. So there are two except sort of strange cases, which are the NF less than NC we treated all together, right? And we saw what happens. Now we treated the NF equal to NC. Now we're going to move to the NF equal to NC plus 1, which will actually be completed by your homework. If you're there doing the homework, if there is one, basically you will fill in the blanks for this theory, because this theory is kind of interesting too. And then we will move on to another class of theory, which probably is the one that is most interesting of them all, which has to do with cyber duality. So there are theories which are conformal and dual to each other and those things. But before I do that, I have to say something about this theory. So here, the classical theory, so the classical modular space, so the classical fields are again M, and then you have the baryons and the antibaryons, which now carry one index only. F prime. Okay, and this could be F prime. Okay. And they obey those funny constraints that I wrote down that I didn't that I wrote down before. Now again, I told you this already. In some ways of writing this B, sometimes you write it as a multi-indices, but then you use the epsilon tensor to get back to this. So I hope you see that this is one way of writing the binders for the NF equal to NC plus 1. Now, I don't want to spend too much time on this theory, but I want to tell you, right. I want to tell you the amazing thing that happens. So the first thing that you could guess, and it's basically what turns out to be true, you would say, what if, so, here, okay, let me say it this way. Here you could have guessed, you looked at the classical modular space here. Let's go back to the NC equal to NF just a second. Suppose you didn't know this. You look at this and you say, well, M and B can both be 0, and it could be interesting to look at the theory where all the vacuum expectation values are 0. You will try to do that and you figure that it doesn't work, and it will tell you that you have actually there is no such, this thing is not on the modular space. Right? Let's go to N plus 1 and C plus 1, and let's try to be naive again and see how about can I set all the M's and the B's to 0? I don't know that. There could be some deformation of the quantum modular of the modular space. If you play around with the dimensions and so on, you actually realize that you can't. So already a first step would be to convince yourself that this kind of thing doesn't work in the NF equal to NC plus 1. So, okay, and this is a game that you can play, and we will not go too much in detail. But then, once you've seen that, then you start asking yourself, maybe these are actually the right degrees of freedom for the theory in the infrared. So could it be that what I would naively expect is actually okay? So could it be that for this theory, could it be that this is probably the least radical of all the theories? This is the theory that you would. This is probably the only theory where you would get something right and using your pre-90s intuition. I mean, this is, it's what it's probably the naivest guess, and it's the only case in which it works, by the way. So could it be that no superpotential is generated? Could it be that the quantum modular space is the same as the classical modular space? And could it be that M, B, and B tilde are the right degrees of freedom at low energy in the infrared? And the answer to this turns out to be yes. So I will not prove that, even in the sort of limited sense of proof that we use in this question, but I will tell you that there is a homework for you to do in which you will convince yourself that it has to be true, and that is because there is a very strong, in this case, a very strong consistency check you can make that works. That is so the answer to all of this is yes. And the consistency check is the 't Hooft anomaly. Match. Now, we talked about anomalies yesterday, and we briefly touched upon the 't Hooft anomaly matching, but so let me say it again. And then I'll leave it to you. So I think I will briefly say this, take a short break, and then we go on until 1:30 sharp. At 1:30, I expect everybody to raise from their table, turn on their chair, and move out, regardless of what I'm doing. Right. So let me just say, so remember the anomaly business, right? You have, for any theory, this is something you use in any theory, supersymmetric or not, whatever metal content it is. You have to look at this 3-point function of the currents, okay? Remember, we have, so the currents, we have gauge, currents. If this guy is anomalous, say, so d Newton 0, okay? If this is anomalous, you're in trouble. The theory is wrong. Sick theory, bad theory. Throw it away. Then you had, suppose you take now a flavor current with 2 gauge currents, and you check for this one whether the flavor current is anomalous. If this one is anomalous, the theory is okay, no problem with the theory, but this current is not conserved. F not conserved. In other words, F is not a symmetry. The group for which, the global symmetry for which F is the current is not a symmetry. It's broken explicitly at the quantum level. This is a typical example of such a thing as the axial anomaly in QED, QCD. Oh, QCD. Then you have, well, this one is silly for us, because G is always simple for us, and a simple group cannot have a trace. The generator of a simple group cannot have trace, so this one is C. And then you would say, what happens to FFF? Right? So what happens if I take 3 flavor currents? This is known as the 't Hooft anomaly. You compute it exactly as far as the anomaly coefficient goes. When you compute the anomaly coefficients, you don't care about whether it's a gauge group or a flavor group. The interpretation is completely different. And that has to do on whether there exist gauge fields that actually give, that give the instanton density that multiplies the particular anomaly coefficient that you can calculate. The calculation of the anomaly coefficient is completely oblivious to what you're going to do with to what kind of group you have. suppose you do it, you compute the anomaly coefficients for these f's, and you find that they're not zero. As far as the theory is concerned, this doesn't do anything. The theory is perfectly consistent, and the symmetry is conserved as well, because there is no gauge field here whatsoever, so the anomaly coefficient has no instanton density to multiply. And so this is actually zero, so when I say non-zero, I mean say the anomaly coefficient is non-zero. Okay, so this trace of TA, TB, TC is non-zero. You can certainly compute that, but it does not mean that the current is not conserved, because the actual full expression here would be that times the instanton density, but there is no instanton density here because there are no gauge fields. Okay, so this is okay. But it tells you something much deeper anyway about how these theories can possibly be related. And this is a brainstorm of Tuft. Well, amazing paper that, to my knowledge, has never been published. There's some lecture notes or something. And the observation is absolutely straightforward, and is the following. Suppose I have a theory in the ultraviolet, some theory in the ultraviolet. For us, it would be super QCD. It would be this guy. Okay, I have an ultraviolet theory, and this theory with a certain flavor symmetry group, GF. And for us, this is SUNF, SUNF, U1, U1. Okay, GF flavor symmetry group. Compute the FFF anomalies, Tuft anomalies. So compute the anomaly coefficient, really, just the anomaly coefficient. There's nothing else to compute. Now, suppose, so this is what you have. And this by itself doesn't tell you anything. Now, suppose that you have a conjecture, you have an argument, you have a belief, you have a hope, you have a wish, that this thing flows in the infrared to some other theory. Right? In QCD, you would go from QCD to effectively like chiral Lagrangians of pions and rho's and so on. Now, this is usually, for an interactive gauge theory, this is a tall order. You can make guesses, but most of the time you don't really, there is a sort of discontinuity of knowledge in the middle where you really don't know what's going on, but you can make educated guesses what's down here. But one thing you can do is the following. Suppose you say, suppose you want to keep the infrared theory to have the same flavor symmetry as the ultraviolet theory. So suppose you guess that this is the infrared theory. Suppose that you wish that you want to have the same as the ultraviolet theory. Then Tuft tells you that the anomalies must match. So you should get the same anomaly contribution in this theory, should be the same as for the ultraviolet theory. And this is a non-trivial check because in the ultraviolet theory you have, say, quarks. You have colored objects transforming in some funny gauge group. In the infrared theory you have bound states. You have baryons, protons, and so on. So, very interesting fact. So there are two options. Either the anomaly matches, in which case you don't prove, but you can say it is possible for these two theories to have the same GF. Or if the anomalies don't match, then GF must be broken somehow. Okay, and this is how you argue that chiral symmetry is broken in QCD. In QCD, if you think this was QCD and this is the infrared theory, then you can argue that there are some subtle points about how many flavors you're using and so on, but basically it doesn't work. So the anomalies don't match, and so you are forced to since you know that QCD is the right theory of baryons, you're forced to conclude that some of the chiral symmetry is broken, okay, which it is, and the pions are the ghost of broken. So in our case, instead, it works the other way around. For an f equal to nc plus 1, and this is your homework, this is exactly what happens, and there is no breaking of the chiral symmetry. So, and this is a consistency check that is very, very strong. When you do it, the first time you do it, you are just sure that it's not going to work. I mean, the numbers are just so weird, but they work. And so since you have something very weird that in principle doesn't look like it's going to work, and then at the end of the day it works, not for all of the anomalies that you can compute, then you believe in the conjecture. Okay. So this is your homework. One of the things. Check all the anomalies. So assume that. So okay, so check all the anomalies. Let me tell you. So here you know what the degrees of freedom are. The fermionic degrees of freedom. So the anomalies come from the fermions, and you know that they are the psi tilde, and the lambda. Okay, and you have to tell me how these guys transform under the GF. What you know, because we did it yesterday. All the flavor symmetry group of these guys. Here, you have to assume that the light degrees of freedom are the fermions contained in these guys here. So you will have to find. So there will be new mesons and so there will be a psi m, which is an NF by NF matrix of fermions that are not transforming under the gauge group. They are only they have the same Glover symmetry, not transforming under the gauge group, completely neutral with respect to the gauge group. Same Glover symmetry. So from that point of view, they could and they do have a 't Hooft anomaly, and you should check. There is this guy, and then there is the one with the baryons, and the one with the antibaryons. In the point of modular space that I have assumed to exist without proof, in which all of these guys are zero, then all of these guys are massless, of course. There is no Higgsing. All of these things should remain if my conjecture is true. Not mine, of course, but if our conjecture is true. These things should be massless and contribute to the anomaly. Compute the anomalies, find the quantum numbers for this, compute the anomaly, and see that they match, and be amazed and happy and then this actually is correct. So this theory has no superpotential, same modular space, and these are the right degrees of freedom in the infrared. Okay? This does not work for an F equal to NC plus 1 or higher, and we will look at that when we come back. Let's take a short break, maybe like 5-10 minutes, and then so because otherwise. So welcome back. There were some questions about where to learn about 't Hooft anomalies and so on. So it's a bit difficult to find the original paper, but if you look at this book, which collects all the 't Hooft's sort of major work in that period, it's called Under the Spell of the Gauge Principle. There are lots of preprints and stuff that at point never been published and so on. That is sort of worth gold. So you learn a lot of physics. So I suggest that you have a look if you're interested. In particular, that preprint is there. So so we have half an hour, 29 minutes to be exact. So I would probably not be able to do the NF much larger than NC plus 1 in full details. I'm not sure whether I want to spill over to the next lecture because I want to start talking about supersymmetry breaking. But I might if I get to the point where I cannot really conclude to my satisfaction. But let's say this way: this part of part A will be a little bit less, well, even less systematic than it has been so far. But you can find some more material in the notes. I did put in a few pages about the Lagrangian limit and how to define the 't Hooft coupling. Completely different issue, but still due to him. But I know that Kostya has already explained everything to you, so I don't have to do that. So instead, I will just jump right in and try to argue what happens. So now we've seen a few cases. Now let's ask ourselves what happens for superQCD when NF is larger than NC plus 1. Well, first of all, let's try to go at the other end. How high can we go? How large can NF be? You can answer this question while I get the chalk, which is finished, by the way, almost finished. You remember that beta 1 is 3nc minus 1, and asymptotic minus nf. And asymptotic freedom requires this to be positive. So nf cannot be, so if nf was too big, in fact, if nf was bigger than 3, so nf must be less than 3nc, because if nf is larger than 3nc, I lose asymptotic freedom, and the theory becomes kind of trivial, because what happens is that the theory becomes infrared free. It's like QED. And you flow into the infrared, you think that something wonderful is going to happen, but the coupling constant instead just gets smaller and smaller and smaller until you get a free theory. So the interesting case is for nf less than 3nc. Okay. So this is, so the region of interest is therefore between this and this. Okay. Now, so we started off with 1 and we worked our way up. Now let's actually start from here. Or in fact, let's start by not committing ourselves to anything and let us write down the 2-loop. Why am I doing this? Beta function. The 2-loop beta function is equal to, not surprisingly, the 1-loop beta function, which we computed before. Well, we did compute we wrote it down and applied the popular group theory, plus the 2-loop coefficient, which I just write down without further ado. This is the exact 2-loop beta function, and then there are, of course, other things. Now, let us try to look at this theory in the large N limit. What do we mean now, large N? Because there are two N's here. There is both flavor and color. So, I mean color. So, I mean, I want to define a tooth coupling, which I hope is the same as Kostia's definition, as G squared and C, and just to make this factors of pi go away, hope I've done it right, we put a 16 pi squared. There's an unfortunate mismatch in the conventions, well, but this is the one that gets you less pi's at the end. I hope you know that the large N limit, I hope you know that the meaning of the large N limit is that if you take a gauge theory with a large gauge group, say SUN, with a very large number of colors, and you do perturbation theory, you think you're doing an expansion in powers of G, which is what you do. But then you realize that every time the G comes, it's multiplied by some factors of N. So really, since it's not G, but it's the overall factor of expansion that has to be small, it turns out that in the large N limit, the actual coupling constant that you should consider is the product of these things. And it turns out that if you let, now these are dimensionless quantities, so I can do whatever I want. If you let NC go to infinity and G go to 0, keeping lambda constant, then you actually pick out a particular type of the diagrams in the theory, which are called the planar diagrams. Did Kostya mention this? Okay, so. If you then redo the scaling here, now I have two N's, so I have an F and an C. So now I also want to see what happens with, with NC. So for that, let me assume that I also want to scale NC as some constant, which is L finite, times NC. Okay.
NF.
Thank you. Otherwise, A would be equal to 1. So this picks out other types of diagram, but it's still, if you have the exact formula here, you don't have to worry about the planar expansion or anything, you can just work it out. And I claim that if you take this definition, the betas become very simple, in fact, and it becomes minus 2. Do it, it's a nice exercise. 3 minus A. You can basically read it off, really. lambda cube, and then it's minus 3 plus 2a. Okay, so this is your new beta function. Okay, and now you would like to study this beta function. So the theory is described by this beta function. Now you realize one thing. So clearly there is always an asymptotically free point if a is less than 3. If a is less than 3, the theory will be asymptotically free, which matches with what we said before, that NF has to be less than 3 and C. Fine. But then there's also this guy. Now, typically, so this guy starts out negative, and this guy, we don't know. But let's say that we pick an A such that this guy is positive. So you could get a situation where the beta function to two loops look like that. And if you look at this point here, is the solution of this equation when you set lambda equal to 0, dropping the thing, and it is equal to 3 minus a divided by 2a minus 3.
I count 3 g's and 2 loops, but then lambda squared.
Or yes, you're right. I was actually yes, yes, you're absolutely right. Yes, it's irritating. I think. I don't know if now I don't know what to do with the pies. Apologies. There is the right thing is
No. Because it's the beta function of lambda and not of g. Because it's the beta function of lambda and not of g. So you.
Thank you. No, it's actually correct. No, that's right. Thank you. No, this is very correct. Good point. This is the beta function of lambda, so you have to do a chain derivative. Thank you.
Okay.
Right. I thought it was a bit, but when I saw it too, I said, no, this can't be right. But of course, there is this extra derivative of lambda with respect to g. Thank you. Right. Right. So what do we do now? Right. So you have this point here. Now, suppose a is equal to, I don't know, 2. Right. Suppose a is equal to 2, then this point is 1 over. Is 1, actually. If a is equal to 2, this point here is 1, lambda equal to 1. Should I trust this point? Should I say that, okay, if this is a 0, then I can say that this is actually an infrared fixed point of the theory. So the theory, if I sit here with the coupling coil, if I start out here in the ultraviolet, then as I flow in the infrared, the beta function will give me here, and this will be a conformal fixed point, conformal field theory now. Right? But can I trust it for a equal to 1? Would you trust me if I tell you that there is a fixed point here at lambda 2 equal to 1, based upon my two-loop calculation? You wouldn't, right? You wouldn't trust me in any way, but in this case, there is even a good reason not to trust me. Is the fact, how do I know that the higher loop corrections do not mess it up? I have truncated my thing here, but if so otherwise I can prove that the theory has an arbitrary number of fixed points just by truncating the beta function to pth loop, and a polynomial usually has a bunch of zeros, and I found some wonderful dynamics between these fixed points. Of course, it's all nonsense, because the only region in which you can trust the perturbative expansion of the beta function is where lambda is very, very small. In fact, strictly speaking, where you can actually have a parameter where parametrically you can make beta, you can make your observable as small as possible, as small as you wish. So, bottom line, you can trust this thing only if this number here is very close to 1. In other words, so if 1 sits here, then it's okay. Then this infrared fixed point will probably exist. And it will exist, actually. And this exists in QCD as well. You can take QCD and you play the same game. This is called the Banks-Sachs fixed point. You can play the same game in ordinary QCD with different number of colors and flavors, and you find that indeed there are some regions where you find this conformal fixed point. So, and in this case, so where A is smaller but not too small, not much smaller than 3, indeed this thing goes to very close to 1. And so this is a fixed point.
0.
So So this is one end of the so-called conformal window. In other words, so if we say that, so NF, remember that NF was supposed to be less than 3 NC. But if NF is less than 3 NC, but not much, but these are both large, and NF is close to 3 NC, then this is going to be there is going to be an infrared fixed point. Okay. This is all you could say if the theory had no supersymmetry. The amazing thing if the theory has supersymmetry is that you can say much, much more. You can say that, and we will not prove all of these things, but I will give you some hints. You can say that, first of all, so it is referred to as the conformal window because there is, even for QCD, there is a range of NF in which the theory flows to a conformal fixed point. Think of this as QCD. In QCD, there are some NF and NC for which this point is very close to the Gaussian point, and you know it's conformal. The question is, how low can NF go until you lose conformality? You know that you lose it somewhere, because when NF is equal to 3 and NC is equal to 3, QCD is not conformal. So you lose it somewhere. The question is where? In non-supersymmetric gauge theory, it's a very difficult question that is being answered hardly by lattice calculations, a lot of work. But in super QCD, here's the answer. That's it. That's the first thing. So you know both the ends of the conformal window. In fact, you can even go down to NC plus 2 in the case where NC plus 2 is less than this, which happens already for NC equal to 4. If this happens to be less than this, which happens for NC equal or larger than 4, then there is even an interesting region here. But let me just focus on this thing here. All right? So in super QCD, you can actually argue that you know where the conformal windows end in this sense, and you can actually show that this is valid outside of the Lagrangian limit. So this is true even for n equal to 4. So it has nothing. You can decouple this argument from the Lagrangian limit. The only thing that connects with the Lagrangian limit is the right end of the conformal window at large n, but everything else is due to all the properties of supersymmetries. Let me argue a little bit on how you would go about proving all of these things. Of course, here there is to do this thing justice, I would need another lecture. But I don't want to go into that. But let me just give you a few things. So first of all, if this is an n equal to 1 theory, and I claim that it's conformal, then the theory will have a super conformal symmetry. Now, super conformal symmetry is an extension of the conformal symmetry. Conformal symmetry, remember, is SO4, 2, which is in itself an extension of the Poincaré of the Lorentz of the Poincaré. So let me just, I don't know what the right symbol is. It's the Poincaré group with the P and the M, the generators of the translation and the rotations and the boosts. And then you add the dilaton operation and the conformal boost KK group. Okay, for those of you who learn the conformal group. If you want the super conformal group, you also have to take the charges, which you had before, the Q's, which are the super Poincaré. Here, you get a nice set of charges. You probably did this with Costi or something. Did Costi mention any of this? Okay, good. So here is simpler because he probably was talking about extended supersymmetry. Here you just get another set of charges, which are called S, and R charge, a bosonic R symmetry, which is the R symmetry that we were talking about before. That is included, must be included for closure of the super Poincaré algebra. I will not tell you what the commutational relations are. This is all stuff that you probably know, and if you haven't, you can learn from the literature. But there is one important point that has to be discussed. is that for, this is an important property of the n equal to 1 superconformal algebra, a chiral primary field. So a primary field is a field that cannot be written as Q or something else. Okay, a chiral primary field, a chiral field. Okay, primary, like a chiral superfield, like the ones that we have, obeys D equal to 3½ R. So if I know the R charge, I know the scaling dimension of this D is the eigenvalue of this operator here. So if I know the R charge, I know the scaling dimension of this field. Now, this actually allows you to, this is amazing, right? Because this is something you wish you had in ordinary non-supersymmetric theories, because if this is a charge, this is additive. And whereas this is the anomalous dimension that requires very complicated regularization, point splitting, and all of these things. But if you have chiral fields, you can just multiply them together. They form something that is called a chiral ring, and you don't have to worry about singularities because they're controlled by these formulas. How about looking then at delta of M? Delta now has become, D has become delta. Oops, in my notes, D is the same as delta, and let me call everything D then. How about D of my M? My M, remember, was, this is now the scaling dimension, okay? This is the one that is not necessarily equal to. Now, if you remember the R charge of M, M is QQ tilde as before, right? I'm not changing anything here. If you remember what the R charges of Q were, you see that 3½ of the R charge of QQ tilde, they're all additive. So this is 3 times 1 minus NC minus NF, divided by NF. Okay? Let's plot this. As a function of NF, I plot D of M. Okay? Now, where do I trust this formula? Well, I trust this formula wherever the theory is conformal. This requires conformal symmetry. If this formula is not true in the other theories that we've seen, because the other theories are not conformal. But if the theory is conformal, then this is true. Okay? Where can this be true? Well, there are two notable points here. There is a point where an F is equal to, guess what, 3 NC, and a point where an F is equal to 3½ NC. If I have written it down right, you can check that at this point D is equal to 1, and that at this point D is equal to 2. Now, away from here, you have lost asymptotic freedom. So you certainly, M will become a free field. And M is nothing but a free field made of free fields. So its dimension will just be the sum in the way in the infrared where the renormalization essentially is nothing, it's nothing because the theory becomes free. M will have the dimension of twice of Q plus the dimension of Q tilde. So this matches with the fact that here there is, so here you would expect this dimension to be just trivially 2. You cannot go below 1 because there is another theorem of superconformal theory. The representations of the superconformal group do not allow for a unitary representation, do not allow for a scale of scaling dimension less than 1. So something must go wrong when you hit this point. However, between this point and this point, you have all possible, you have values for this thing that are in principle allowed. Okay, so again, Seidler get the brilliant idea of saying, well, look, maybe that's what it is. Maybe between these two values of NF, this is an F, maybe between these two values of NF, the infrared theory, so that was the conjecture that he had, or the idea, so maybe for NF between these two magic numbers, M survives in the infrared. It survives. So, in the infrared, as an interacting interacting field in the conformal theory. And now the question is, well, okay, but then M by itself certainly will not define a conformal field theory. So what kind of conformal field theory is it? And here it takes a little bit of courage, and then once you find the right answer, then there are many ways of checking that you got it right. But once you say M is going to be there, M is going to survive, what else is going to be there? Well, it's not going to be the same theory as before, for sure. There's going to be something completely different. But since you know that the global symmetry has to match from the infrared, from the ultraviolet to the infrared, you would like to construct what else? So what else can be there? We want to find something else that has the same global symmetries as the previous, as the theory in the infrared. So let us say, well, what kind of theories do you know in four dimensions? It's got to be a gauge theory. Let's say it's a gauge theory. So there will be some gauge group G, which I have no idea what it is, and it's not SU and C. Let's say it's there. And then there will be some fermions, but these fermions will have to fill an NF, sorry, not fermions, some chiral superfields. Let me call them little q and little q tilde, and they will have to be transforming under some representation of G, and there will be NF of them, because I need the same global symmetries to be matched. So maybe I can make up a theory that in fact becomes conformal in the infrared and is matched to this one. And yes, the answer is yes. And a little bit of thought actually shows you that although it's a very, very daring conjecture to make at first, the only group that could possibly work, let's call it G dual. So G dual, the only group that could possibly work is SU NF minus NC. Because you want something, if you look at the beta function of this guy, you see that it kind of behaves exactly the opposite way as the beta function of the one that we had before. Whereas this one was, the ultraviolet theory was becoming infrared free, the infrared point was becoming almost free in this region. This one has the property of becoming infrared almost free in this region. So they are kind of dual to each other. So the idea is that this theory, which you can prove just by large N limit, has a conform with these Q's, all right? This theory with Q and Q tilde in the fundamental and anti-fundamental of this gauge group and F of them, plus something that was not there before, a new object, a meson field, that is completely neutral with respect to the gauge group and transforming in the same global symmetries as before. You can show that this theory is actually what you flow to in the infrared. So in a sense, this theory and the other ones are dual. There is an extra, the cherry on the top is to realize that actually these degrees of freedom are a little bit too many, because I could also make a meson out of these guys. I could make a Q tilde, and that would be too much. You can even check anomaly matching and all these things. But you can get rid of this guy by adding a superpotential, which is the trace of Q tilde M. All right? And so when you take the F terms with respect to M, you force this extra meson to be zero. And you can even check that the dual of the dual is zero, is the same, and so on. So this is known as cyber duality, and this is where I conclude. So in the conformal windows where NF is between 3/2 NC and 3 NC, there are two completely different theories with two completely different gauge groups, but that sort of flow to the same point in the infrared, and they're sort of dual to each other. You can match one to the other by going from NF to from NC to NF minus NC. So you have sometimes it's called the ultraviolet theory or the electric theory. There's a whole, So where the gauge group is S and C, and you have the fields are the Q's and the Q tildes. And there is let's say there's theory number 1. It's called the electric theory sometimes. Theory number 1. And theory number 2 is the one that we have, that I just presented by sketching all of these arguments. Everything can be made much, much more reasonable and sensitive than what sensible than what I've said now. But it's this was a surprise really. Although everybody knew that the gauge group in itself is not really an observable quantity. You could, but this is really a very dramatic case of the theory changing gauge group kind of thing. So you have a different gauge group. The fields are Q, Q tilde, and M. Well, M is a singlet with respect to this gauge group, and these behave exactly the same way. And whereas here you have the superpotential was 0, here the superpotential is equal to the trace, some constant that you can actually play with, times Q, Q tilde M. And so I have 1 minute. So obviously this is a rushed, I rushed through probably what is the most interesting thing about all of these dualities, namely that window, this window here. Much more could be said. But we can take up a little bit if you want in the discussion, but instead I want to now conclude part A with this sort of rush summary of this window, and tell you that next time we start part B, which has to do with supersymmetry breaking. So we will look at theories where which are completely different in a sense, and then break supersymmetry. These are of course theories that we like also for phenomenological reasons, because supersymmetry, if it is realized in nature, has to be broken. Okay, so let's go in.